Reducing work and eliminating excise. Digital products too often contain interactions that are top heavy, requiring unnecessary work for users. Interacting with an interface always involves some work on the part of the user. The goal of designers, or at least one of the more important ones, is to minimize the work while at the same time enabling users to achieve their goals. If designers and developers don't pay careful attention to the human actions required to operate their technology, the result can be a taxing experience for the users. They will struggle to relate their mental models of the activities they want to perform to product interface that has been engineered. Users perform four types of work when interacting with digital products: cognitive work, comprehending product behaviors as well as text and organizational structures; memory work, recalling product behaviors, commands, passwords, names, and locations of data objects and controls, and other relationships between objects; visual work, figuring out where the eye should start on the screen, finding one object among many, decoding layouts, and differentiating among visually coded interface elements such as list items with different colors; physical work, keystrokes, mouse movements, gestures, click, drag, double click, switching between input modes and number of clicks required to navigate. When implementation model thinking is applied to digital products, these four types of work are seldom minimized for users. Quite the opposite, in fact, the result is software that, in effect, charges its users a tax or excise of cognitive and physical effort every time it is used. In the physical world, mandatory tasks that don't immediately satisfy our goals are sometimes unavoidable. For example, when we get up late on a workday and need to get the office quickly, we must open the garage door, get in the car, start the motor, back out, and close the garage door before we even begin the forward motion that will take us to our destination. These actions support the physicality of the automobile rather than getting us to the destination faster. If we had Star Trek transporters instead, we'd dial up our destination and teleport there instantaneously. No garages, no motors, no traffic lights. Digital products, much like our fictional transporter, don't necessarily need to have the same kind of roadblocks that stand in the way of our goals in the physical world. But implementation model design often makes it seem that way to users. Goal directed task versus excise task. Any large task, such as driving into the office, involves many smaller tasks. Some of these tasks work directly toward achieving the goal. These are tasks like steering down the road toward your office. Excise tasks, on the other hand, don't contribute directly to reaching the goal, but instead represent extra work that satisfies either the needs of our tools or those of outside agents as we try to achieve our objectives. In this example, the exercise tasks are pretty clear. Opening the garage door is something we do for the car, not for us, and it doesn't move us toward our destination the way the accelerator pedal and steering wheel do. Stopping at red lights is something imposed on us by our society that, again, doesn't help us achieve our true goal. In this case, it does helps us achieve a related goal of arriving safely at our office. A tune-up helps keep the car running well, but it doesn't get us anywhere quickly while we're doing it. Software 2 has a pretty clear dividing line between goal-directed task and exercise task. Like automobiles, some software exercise tasks are trivial and performing them is no great hardship. On the other hand, other software exercise tasks are as obnoxious as fixing a flat tire. Installation leaps to mind here, as do such exercise tasks as configuring networks and backing up files. Types of exercise. The problem with exercise tasks is that the effort we expend doing them doesn't go directly toward accomplishing our goals. Where we can eliminate excess tasks, we make people more effective and productive, ultimately creating better usability and a better user experience. Design principle: eliminate excess wherever possible. The existence of excess in user interfaces is a primary cause of user dissatisfaction with software enabled products. It behoves every designer and product manager to be on the lookout for interaction excess in all its forms and to take the time and energy to see that it is eliminated from their products. Navigational excise. Navigational through the functions or features of a digital product is a largely excise, except in the case of games where the goal is to navigate successfully through a maze of obstacles. The work that users are forced to do to get around in software and on websites is seldom aligned with their needs, goals, and desires. However, well-designed navigation can be an effective way to instruct users about what is available to them, which is better aligned with their goals. Unnecessary or difficult navigation is a major frustration to users. In fact, in our opinion, poorly designed navigation presents one of the largest and most common problems in the usability of interactive products, mobile, desktop, web, or otherwise. It is also the place where the developer's implementation model typically is made most apparent to users. Navigation through software occurs at multiple levels, across multiple windows, views, or pages, across multiple panes or frames within a window, view, or page, across tools, commands, or menus, within information displayed in a pane or frame such as scrolling, panning, zooming, following links. We find it useful to think in terms of a broad definition of navigation: any action that takes the user to a new part of the interface or that requires him or her to locate objects, tools, or data elsewhere in the system. When we start thinking about such actions, such as navigation, it becomes clear that they are excised and therefore should be minimized or, if possible, eliminated. The following sections discuss each of these types of navigation in more details. Navigation across multiple screens, views, or pages. Moving across multiple application views or pages is perhaps the most disorienting kind of navigation for users. It involves a gross shifting of attention that disrupts the user's flow and forces him into a new context. The act of navigating to another window also often means that the contents of the original window are partly or completely obscured. On the desktop, it means that the user needs to worry about window management, an excise task that further disrupts his flow. If users must constantly shuttle between windows to achieve their goals, their disorientation and frustration levels will rise. They will become distracted from the task at hand and their effectiveness and productivity will drop. If the number of windows is large enough, the user will become sufficiently disoriented that he may experience navigational trauma. He gets lost in the interface. Sovereign posture applications, discussed in Chapter 9, can avoid this problem by placing all main interactions in a single primary view, which may contain multiple independent panes. Navigation between panes. Windows or views can contain multiple panes, adjacent to each other and separated by splitters. See Chapter 20, or stacked on top of each other and denoted by tabs. Adjacent panes can solve many navigational problems because they provide useful supporting functions, links, or data on the screen in close reach of the primary work or display area. This reduces navigation to almost nil. If objects can be dragged between panes, those panes should be adjacent. Problems arise when adjacent supporting panes become too numerous or are not placed on the screen in a way that matches users' workflows. Too many adjacent panes result in visual clutter and confusion. Users do not know where to go to find what they need. Also, crowding forces scrolling, another navigational hit. Navigation within the single screen thus becomes a problem. Some web portals, trying to be everything to everyone, have such navigational problems. In some cases, depending on user workflows, tab panes can be appropriate. Tab panes bring with them a level of navigational excise and potential for user disorientation because they obscure what was on the screen before the user navigated to them. However, this idiom is appropriate for the main work area when multiple documents or independent views of a document are required, such as Microsoft Excel. Figure 12.1, Microsoft Excel makes use of tab panes visible in the lower left to let users navigate between related worksheets. Excel also makes use of splitters to provide adjacent panes for viewing multiple distant parts of a single spreadsheet without constant scrolling. Both these idioms help reduce navigational exercise for Excel users. Some developers use tabs to break complex product capabilities into smaller chunks. They reason that using these capabilities will somehow become easier if the functionality is cut into bite-sized pieces. Actually, putting parts of a single facility onto a separate panes increases access and decreases users' understanding and orientation. The use of tab screen areas is a space-saving mechanism and is somewhat necessary to fit all the required information and functions into a limited space. Settings dialogues are a classic example. We don't think anyone is interested in seeing all the settings for a sophisticated application laid bare in a single view. In most cases, though the use of tabs creates significant navigational exercise, it is rarely possible to accurately describe the contents of a tab with a succinct label, though in a pinch, rich visual modeless feedback on tabs can help. See Chapter 15. Therefore, users must click through each tab to find the tool or piece of information they are looking for. Tab panes can be appropriate when there are multiple supporting panes for a primary work area that are not used at the same time. The support panes can be stocked and the user can choose the pane suitable for his current task, which is only a click away. A classic involves the color mixer and swatches area in Adobe Illustrator as shown in Figure 12.2. These tools are mutually exclusive ways of selecting a drawing color, and users typically know which is appropriate for a given task. Figure 12.2, Tab Palette in Adobe Illustrator allows users to switch between the mixer and swatches, which provide alternative mechanisms for picking a color. Navigation between tools and menus. Another important and overlooked form of navigation results from a user's need to use different tools, palettes, and functions. Spatial organization of these within a pane or window is critical to minimizing extraneous mouse movements that at best could result in user annoyance and fatigue, and at worst could result in repetitive stress injury. Tools that are used frequently and in conjunction with each other should be grouped spatially and also be immediately available. Menus require more navigational effort on the part of users because their contents are not visible prior to clicking. Frequently used functions should be provided in toolbars, palettes, or the equivalent. Menu should be reserved for infrequently accessed commands. We discuss organizing controls again later in this chapter, and we discuss toolbars in depth in Chapter 18. Adobe Photoshop exhibits some undesirable behaviors in how it forces users to navigate between palette controls. For example, the Paint Bucket tool and the Gradient tool each occupy the same location on the tool palette. You must select between them by clicking and holding the visible control, which opens a menu as shown in Figure 12.3. However, both are field tools, and if both are used frequently, it would be better to place each of them on the place next to each other to avoid the frequent flow-disrupting tool navigation. Figure 12.3, in Adobe Photoshop, the Paint Bucket tool is hidden in a combo icon button. See Chapter 21 on its tool palette. Even though users make frequent use of both the Gradient tool and the Paint Bucket tool, they are forced to access this menu anytime they need to switch between these tools. Navigation of information. Information or the content of panes or windows can be navigated using several methods: scrolling, panning, linking, jumping, and zooming. The first two methods are common. Scrolling is ubiquitous in most software, and linking is ubiquitous on web, although increasingly linking idioms are being adopted in non-web applications. Zooming is used primarily to visualize 3D and detailed 2D data. Scrolling is often a necessity, but the need for it should be minimized when possible. Often there is a trade-off between paging and scrolling information. You should understand your user's mental models and workflows to determine what is best for them. In 2D visualization and drawing application, vertical and horizontal scrolling are common. These kinds of interfaces benefit from a thumbnail map to ease navigation. We'll discuss this technique as well as other visual signposts later in this chapter. Linking is the critical navigational paradigm of the web. Because it is a visually dislocating activity, extra care must be taken to provide visual and textual cues that help orient users. Zooming and panning are navigational tools for exploring 2D and 3D information. These methods are appropriate when creating 2D or 3D drawings and models or for exploring representations of real-world 2D and 3D environments, architectural walkthroughs, or topographic maps, for example. They can fall short when they are used to examine arbitrary or abstract data presented in more two dimensions. Some information visualization tools use zoom to mean display more attribute details about objects, a logical rather than spatial zoom. As the view of the object enlarges, attributes, often textual, appear superimposed over its graphical representation. This technique works great when the attributes in questions are tightly associated with spatial data, such as that employed in Google Maps. See Figure 12.4. But for abstract data spaces, this kind of interaction is almost always better served through an adjacent supporting pane that displays the properties of selected objects in a more standard readable form. Figure 12.4, the Google Map app makes excellent use of combination of a spatial and logical zoom. As the user physically zoom in by spreading his fingers apart on the map, location details such as transit lines, traffic congestion, street names, and places of business also come into view. Zoom usually works best when applied to a concrete rather than abstract data spaces such as maps. Panning and zooming, especially when paired, create navigational difficulty for users. Although this situation is improving due to the prevalence of online maps and easy to grasp gestural interfaces, it is possible for people to get lost using virtual spaces. Humans are not used to moving in an unconstrained 3D environments, and they have difficulty perceiving 3D properly when it is projected on a 2D screen. See Chapter 18 for more on 3D manipulation. Skeuomorphic excise. We're experiencing an incredible transformation from the age of industrial mechanical artifacts to an age of digital information objects. It is only natural for us then to try to draw on the models and forms of an earlier era that we are comfortable with and use them in this new, less certain one. As the history of the Industrial Revolution shows, the fruits of new technology can only be expressed at first with the language of an earlier technology. For example, we called railroad engines iron horses in automobiles, horseless carriage. Unfortunately, this imagery and language color are thinking more than we might admit. Naturally, we tend to use old-style mechanical representations in our new digital environments, a practical called skeuomorphism. Sometimes this appropriation of the old is valid because the function is identical, even if the underlying technology is different. For example, when we translate the process of typing with the typewriter into doing word processing on a computer, we are using a mechanical representation of a common task. Typewriters use little metal tabs to rapidly move the carriage several spaces until it came to rest on a particular column. The process, as a natural outgrowth of the technology, was called tabbing or setting tabs. Word processors also have tabs because their function is the same. Whether you are working on a paper rolled around a platen or on images on a video screen, You need to rapidly slew to a particular margin offset. More often, however, mechanical representations shouldn't be translated verbatim into the digital world. We encounter problems when we bring our familiar mechanical artifacts into software. These representations result in excise and unnecessarily limit interactions that could be far more efficient than those allowed for by the old models. Mechanical procedures are usually easier to perform by hand than they are with digital products. Consider a simple contact list. If it's faithfully rendered on screen like a little bound book, it will be much more complex, inconvenient, and difficult to use than the physical address book. The physical address book, for example, stores names in alphabetical order by last name. But what if you want to find someone by her first name? The mechanical artifact doesn't help you. You have to scan the pages manually. The faithfully replicated digital version wouldn't search by first name either. The difference is that on the computer screen, you lose many subtle visual and tangible cues offered by the paper-based book, bent page corners, penciled in notes. Meanwhile, scroll bars, swipe to delete, and navigational drill downs are harder to use, harder to visualize, and harder to understand than simply flipping pages. Designers paint themselves into a corner when they rely on slavishly skeuomorphic metaphors. Visual metaphors such as desktop with telephones, copy machines, staplers, and fax machines or file cabinets with folders in drawers may make it easy to understand the relationships between interface elements and behaviors. But after users learn these fundamentals, managing the metaphor becomes an exercise in excise. For more discussion on the limitations of visual metaphors, see Chapter 13. Screen real estate consumed by skeuomorphic representations is also excessive, particularly in sovereign posture applications, where maximizing screen space for content rather than UI Chrome is of primary importance. The little telephone that so charmingly told us how to dial on the first day long ago is now just a barrier to quick communication. It's all easy it's all too easy to fall into the trap of skeuomorphic excess in the name of user friendliness. Apple's iOS veered uncomfortably in the direction of skeuomorphism for version 4, 5, and 6, but it seems to have finally snapped out of it in iOS 7 as shown in Figure 12.5. Figure 12.5 in iOS 6 left, Apple indulged in some excesses of skeuomorphism that seem to have been purged in iOS 7, which is right. Modal excise. The previous chapter introduced the concept of flow, whereby a person enters a highly productive mental state by working in harmony with their tools. Flow is the natural state, and people enter it without much prodding. It takes some effort to break into flow after someone has achieved it. Interruptions like ringing telephone will do it, as will a model error messages or confirmation dialog. Some interruptions are unavoidable, but interrupting the user's flow for no good reason is stopping the proceedings with idiocy and is one of the most disruptive forms of excise. Design principle: don't stop the proceedings with idiocy. Poorly designed software makes assertions that no self respecting individuals would ever make. It states unequivocally, for example, that a file doesn't exist merely because the software is too stupid to look for the file in the right place, and then it implicitly blames you for losing it. An application cheerfully executes an impossible query that hangs up your system until you decide to reboot. Users view such software behavior as idiocy and with just cause. Errors, notifiers, and confirmation messages. There are probably no more prevalent excise elements than error messages and confirmation messages dialogues. These are so ubiquitous that eradicating them takes a lot of work. In Chapter 15, we discuss these issues at length, but for now, suffice it to say that they are high in excise and should be eliminated from your applications whenever possible. The typical modal error message is unnecessary. It either tells the user something he doesn't care about or demands that he fix a situation that the application can and should usually fix just as well. Figure 12.6 shows an error message box displayed by Adobe Illustrator 6 when the users try to save a document. We're not exactly sure what it's trying to tell us, but it sounds dire. The message stops an already annoying and time consuming procedure, making it even longer. A user cannot fetch a cup of coffee after telling the application to save his artwork because he might return only to see the function incomplete and the application mindlessly holding up the process. We discuss how to eliminate these sorts of error messages in Chapter 21. Figure 12.6. This ugly useless error message box stops the proceeding with idiocy. You can verify or identify what it tells you, and it gives you no options for responding other than to admit your own culpability by clicking OK. These messages come up only when the application is saving. This message come up only when application is saving when you have entrusted it to do something simple and straightforward. The application can even save a file without help and it won't tell you what it needs. Figure 12.7 shows another frustrating example, this time from Microsoft Outlook. Figure 12.7, here's a horrible confirmation box that stops the proceedings with idiocy. If the application is smart enough to detect the difference, why can't it correct the problem itself? The options the dialog offers are scary. It is telling you that you can explode what one of two boxes. One contains garbage and the other contains the family dog. But the application won't say which is which, and if you click cancel, what does that mean? Will it explode your dog? The dialog is asking you to make an irreversible and potentially costly decision based on no information whatsoever. If the dialog occurs just after you change some rules, doesn't it stand to reason that you want to keep them? And if you don't, wouldn't you like a bit more information, such as exactly what rules are in conflict and which of them are the more recently created? You also don't have a clear idea what happens when you click cancel. Are you canceling the dialog and leaving the rules mismatch? Are you discarding recent changes that led to the mismatch? The kind of fear and uncertainty that this poorly designed interaction arouses is in users is completely unnecessary. We discuss how to improve this kind of situation in Chapter 21. Making users ask permission. Back in the days of command lines and character-based menus, interfaces directly offered services to users. If you wanted to change an item such as your address, first you have to ask application for permission to do so. The application would then display a screen where you could change your address. Asking permission is pure excise, and unfortunately things haven't changed much. If you want to change one of your saved address on Amazon.com, you have to click a button and go to a different page. If you want to change a displayed value, you should be able to change it right there. You shouldn't have to ask permission or go to a different room. Design principle, don't make users ask permission. As in the preceding example, many applications have one place where the values such as file names, numeric values, and selected options are displayed for output, and another place where user input to them is accepted. This follows the implementation model, which treats input and output as different processes. A user's mental model, however, doesn't recognize a difference. He thinks there is the number, I'll just click it and enter a new value. If the application can accommodate this impulse, it is needlessly inserting excise into the interface. If the user can modify options, he should be able to do so right where the application displays them. Design principle, allow input wherever you have output. The opposite of asking permission can be useful in certain circumstances. Rather than asking the application to launch a dialog, the user tells a dialog to go away and not return. In this way, the user can make an unhelpful dialog stop budging him even though the application mistakenly thinks it is helping. Microsoft Windows now makes heavy use of this idiom. If a beginner inadvertently dismisses a dialog and can figure out how to get it back, he may benefit from another easy to identify safety net idiom, a prominent place a helpful help menu item saying bring back all dismissed dialogues, for example. Excise is contextual. One man's or persona's goal-directed task may be another excise task in a different context. In general, a function or action is excised if it is forced on the user rather than made available at his discretion. An example of this kind of function is window management. The only way to determine whether a function or behavior such as this is excised is by comparing it to personas goals. If a significant personas needs to see two applications at a time on the screen to compare or transfer information, the ability to configure the main window of the applications so that they share the screen space is not excised. If your personas don't have this specific goal or need, the work required to configure the main window of either application is excise. Excise may also vary by software posture, see Chapter 9. Users of transient posture application often require some instruction to use the product effectively. Allocating screen real estate to this effort typically does not contribute to excise in the same way as it does in sovereign posture applications. Transient posture applications are in use frequently, so their users need more assistance understanding what the application does and remembering how to control it. For sovereign posture applications, however, the slightest excise becomes agonizing over time. However, some types of actions are almost excised and should be eliminated under all circumstances. This includes most hardware management tasks that software could handle itself if a more design and engineering cycles were spent on it. Any demands for such information should be struck from user interfaces and replaced with more silently intelligently application behavior behind the scenes.